In this video, we're going to look at an example question of calculating the expected value of perfect information, the EVPI. So here's the question. We have three different states of nature, Sj for j equals 1, 2, 3, and each of those states has a corresponding probability. So the probability, this is the top table, the probability that we're in state 1 is 0.2. The probability that we're in state 2 is 0.4. The probability we're in state 3 is also 0.4. And then given these different probabilities of states happening, you have to choose between four different actions. These are the A1, 2, A3, and A4. Now each action has a different payoff depending on which state you're in, and that's given by the matrix, the matrix down below. So if you read this, the first number in the first column, 15, that tells you that if you choose action 1 and the world is in state 1, then your payoff is 15. If you choose action 1 and the world is in state 2, your payoff is 19. If you choose action 1 and the world is in state 3, your payoff is 6. And so on. Obviously, the higher the number, the better. So actions with high payoffs are preferable to actions with low payoffs. And then part A asks us, which action has the highest expected payoff? So what we need to do is for each action, we're going to work out the expected payoff. So the expected payoff of action I, EAI, is the sum of the probabilities multiplied by the payoff. And that's for each of the different states. So we're summing it over J. This is the fancy mathematical way of writing this. The expected payoff of action I is the sum from J equals 1 to 3 of the probabilities J multiplied by the payoff of row I. Okay, so actually it's a lot clearer if we just do an example. So the expected value of action 1 is, we're going to go along row 1 of the matrix, and we're going to do the probability of state 1, which is 0.2. We're going to multiply that by the payoff of action 1, state 1, which is 15. And then so we get 0.2 times 15. We're going to keep working on the row. So then we get 0.4. That's the probability of state 2, multiplied by the payoff of action 1 at state 2, which is 19. And keep going 0.4 times 6. And so the expected value of action I is just this calculation, which I believe comes to 13. That's the expected value of action 1. For action 2, we're going to do the same, but for the second row. So the expected value of action 2 is 0.2 times 4 plus 0.4 times 13 plus 0.4 times 10. So we're just going to do the sum of our probabilities multiplied by our payoffs, and this now comes to 10. Keep going for expected value of action 3. 0.2 times 1 plus 0.4 times 4 plus 0.4 times 2, and that is 2.6, I believe. Yep, and then finally, the expected value of action 4 is 0.2 times 13 plus 0.4 times 13 plus 0.4 times 10, and this is 11.8. Okay, so the question part A, which action has the highest expected payoff? Well, the first one has a payoff of 13, so A1 with payoff, expected payoff is equal to 13. So that was the highest of those expected payoffs. And now this maximum expected payoff is called the EMV. EMV, the expected monetary value. So that's which is the maximum over all of our options of the expected payoff of the given action. So it's the maximum expected payoff over all of our values of I. So in this case, it's 13. That's the EMV of this payoff matrix. Okay. Now part B asks us about the expected value of perfect information. Now the key thing is that in part A we had to choose an action knowing, well, we didn't know what state the world was in, we just knew the probability of different states. If we have perfect information, not only do we know we actually know what state the world will be in. Each state still has that same probability, but if the world is in state 1, we know it's in state 1. So we can just, each time we can choose the best action. So if the world's in state 1, we would just choose action 1 because that has the highest value in the first column. If the world's in state 2, we would just choose action 1 again, because again, that's the highest value in the second column. If the world's in state 3, it doesn't really matter whether we choose action 2 or action 4, because again, they each have the maximum value in the third column. So this lets us calculate what's called the EV, the expected value given perfect information, which is the sum of the probabilities, the PJs, multiplied by the maximum of the payoff matrix in each column. And we're going to sum over, this is summing over J, which is each column. So we sum over, for each column, we take the probability of the column and multiply by the maximum of the numbers in that column. So again, so the first column is 0.2, and the maximum value in the first column is 15. The second column, the probability of S2 is 0.4, and the maximum value in the second column is 19. And then S3, again, it's 0.4 is the probability, and the maximum value in the third column is 10. So this EV given PI, we did this calculation, 0.2 times 15 plus 0.4 times 19 plus 0.4 times 10. I think if you work that out, you get 14.6. So that's the expected value you would get if you had perfect information. You knew what state we were in. Sort of. And so to choose the optimum action in each state. Now, the question doesn't ask for the expected value given perfect information, it asks for the value of the perfect information itself. So that is the difference. So EVPI is the difference between the expected value given perfect information and the expected monetary value. So it's the additional value obtained by having perfect information. So in this case, it's 14.6 minus 13. So the expected value of perfect information is 1.6.